Hey, there's a new sugarcane juice store near our school. I got a bottle of it right here, but I saw a lot of waste bagasse being produced, so I feel guilty.
Actually, bagasse waste can be used to absorb heavy metal ions.
I have heard that nanocellulose can be synthesized from bagasse and used to absorb heavy metal ions more effectively though.
Let's experiment and find out.
Wash bagasse waste and grind it into powder. Heat it with nitric acid to increase its absorption capacity, then sodium hypochlorite for delignification, and again using sodium hydroxide to remove hemicellulose. Lastly, dry the mixture to obtain nanocellulose. To compare the absorption capacity of unrefined bagasse, bagasse powder, and nanocellulose of mercury 2, lead 2, and copper 2 ions, we add mercury 2 chloride to a sample of each adsorbent and stir. Filter and add potassium iodide into the filtrates. Filter out the precipitate and repeat the steps using lead 2 nitrate. The mass of the precipitates were measured and compared with the control. We found nanocellulose has the highest adsorption capacity of lead 2 ions. For copper 2 ions, stir copper 2 sulfate with each sample of adsorbents. Filter and add ethane 1,2-diamine into the filtrates to form a purple complex. Use a calorimeter to measure the absorbance of the solutions and compare results with the control. The solution treated with nanocellulose has the lowest absorbance, meaning nanocellulose is most effective in adsorbing copper 2 ions. We add sulfuric acid to the used adsorbents to regenerate them. The nanocellulose turns from blue back to white, indicating the nanocellulose is regenerated. The pale blue color of the washings show copper 2 ions are recovered. The steps used before in colorimetric analysis are repeated using the regenerated adsorbents. The paler purple color of the complex for nanocellulose shows it's more effective in adsorbing copper 2 ions after regeneration. The results also show that the regenerated nanocellulose is effective in adsorbing copper 2 ions even after round 3 of ion adsorption. To produce biofilm, nanocellulose is combined with different amounts of PVA, glycerol, and citric acid. We test the tensile strength by measuring the force required to rip each biofilm apart with a spring balance. Water absorption ability by measuring the percentage by mass increase after being soaked in water, and flexibility of the 10 blends. The blend with a combination of nanocellulose to PVA to glycerol at the ratio 10:6:1 shows the highest flexibility and has high enough tensile strength that allows it to be stretched without breaking. It also shows low water absorption ability, which keeps it from absorbing and dissolving in water.
So after adding these treatments, nanocellulose synthesized from sugarcane bagasse can really absorb heavy metal ions for multiple rounds more effectively than bagasse.
It can even be used to create biofilm as a cling film replacement.
It's both environmentally friendly and useful.